So, good evening. Today, I'll conduct your week 4 problem solving and doubt clearing session for the subject electrical instruments and measurements. Okay. So, I'll share my screen. So, I will start with the recap of week 4. And then we will see. So, what was the topic which Sir covered in week 4? One was energy meter. So, can you tell an application why we require the energy meter? Where do you think an energy meter
measure to measure power, sir.
measure power? But where? In your house, where will you want to measure the power?
In our house, sir, in a plant area.
Okay. So the energy meter is used to measure the units of energy which each flat or house is using. Okay. So every month it will measure how many units you're using, and based on that, it will calculate how much money you have to pay, and you will get an electricity bill. Okay, you will get an electricity bill based on that. So now, sir taught about the energy meter, like how it requires a moving magnetic field, etc., has to be generated. And once the magnetic field is generated, you once the field is generated, how using that field which is generated, you can measure how much energy is being taken. Okay, so what do we use a wattmeter for? Hmm? Anyone? Niranjan, Mutazagi, Manchini Devi. What do we use a wattmeter for? You can also write in the chat. Okay, you guys are very shy. So wattmeter is used to measure power. And an energy meter, we use it to measure energy. So what is the unit of power? Unit of power is in watts. What is the unit of energy? Hmm? Anyone has any idea?
Volt ampere.
Sorry?
Volt ampere, sir.
Volt ampere? No. Volt ampere is actually your apparent power. Your energy actually is your power into your second. Either it could be watt into second, or it could be watt per minute, watt into minute, or it could be watt hour. Watt hour is a common way used to measure how much energy or power energy you're consuming. Okay. So actually energy is basically your integration of power into time. Okay. So how much power you're using for how much time you're using, that basically refers to how much energy is being consumed by your house or by you or by some particular application or some particular appliance. So a wattmeter and energy meter, they have similar roles. So wattmeter will measure how much power is being consumed. Energy meter will measure how much energy is being used. So now, suppose I have some supply, some voltage supply, and you have some load. Now, if you want to measure the power, what do? Is you will connect a wattmeter. So wattmeter will have a current coil. Then the wattmeter also will have a pressure coil. So this entire thing becomes your wattmeter. This is your current coil. This is your pressure coil. And we know that for wattmeter method, what it does is it finds the average of your voltage into current. It will find the average of that voltage into current, and that is your average power which is being used. But now, when we have to use an energy meter, what an energy meter will do is it has to find the voltage into current into how much time is also going. Okay, it is with respect to time. So the energy meter will also have the same connection as the watt meter. Not similar, it has the same connection. Hmm. So that was touched upon by Sir. So any doubts still here?
No, sir.
Okay. So that was there. Then Sir also talked about a three-phase power measurement. So the AC supply which comes to your house, is it single phase or three phase?
Single phase.
Sorry?
Single phase, sir.
Single phase, okay. Yeah, so usually to most houses, it will come at your socket, it will come as a single phase thing. But sometimes what happens is there comes the three phases will come to your building. Then some flats get from phase A, some flats will get from phase B, some flats will get from phase C. So what happens is when there's a fault in one phase, the other two phases will work, will continue to work. So then some flats will not have power, some flats will have power. I don't know if you have come across that. Okay. So three-phase power, three-phase supply can also come to your building, can also come to your flat, but necessarily will not come to your apartment. So it's a different case in case you have your own bungalow or something where you're getting direct three-phase supply. So now in three-phase, what do we have is we have one voltage source here, another voltage source here, another voltage source here. So these are all phase shifted from each other by 120 degree. Okay. Now they are all connected to some load. Okay. So this is your three-phase load. This is your three-phase supply. So now if you want to measure power, what you can do is you can, there is some certain current, let's just say this is current IA, this current IB, this some current IC. Okay. And this is the voltage VA, this is the voltage VB, and this is the voltage VC. Okay. So your power is actually VA into IA plus VB into IB plus VC into IC. So what has Sir told? How do we measure this power? Does anyone remember from the lectures? You guys are going through the lectures, I hope, right? So there's one case in which we can have a wattmeter for each phase. We can have a wattmeter for each phase, and we can measure the voltage and current, and thus we can get the power in each phase. Or there's another method in which this is your wattmeter 1, and this is your wattmeter 2. Okay. So using only 2 wattmeters, you can measure 3-phase power. This is in case when there is no return part. When it is a 3-phase 3-wire connection, you can use 2 wattmeters and you can measure 3-phase power. So this is the current coil of wattmeter 1. This is the voltage coil of wattmeter 1. This is the current coil of wattmeter 2, and this is the current, and this is the pressure coil of wattmeter 2. So if you see, wattmeter 1 is measuring IA into your VAB. So it is actually measuring IA into VA minus VB. What is your wattmeter 2 measuring? The current coil is measuring current IC. So it is IC. And what is your pressure coil measuring? It is measuring what is VC to B. Okay, so it is VCB. So actually it is measuring IC into VC minus VB. Any doubts in this? Okay, if there are no doubts. Okay. Now, next page. So my W1 plus W2 becomes equal to IA into VA minus VB plus IC into VC minus VB. So it is IA into VA minus IA into VB plus IC into VC minus IC into VB. So that is equal to IA into VA plus IC into VC minus VB into IA plus IC. What can we write IA plus IC as? If you see this node over here, it is actually IA and IC is also coming. IA and IC are coming here. So IA plus IC plus IB is equal to 0. Over here, we know that IA plus IB plus IC is equal to 0. So we can also write IA plus IC is equal to minus IB. That's why W1 plus W2 is equal to IA into VA plus IC into VC minus VB into minus IB. So it actually is equal to IA into VA. The minus and minus becomes plus. So this plus IB into VB plus IC into VC. So using like this, the 2 wattmeters, you're able to measure 3-phase power. But you must remember, this kind of connection is important. You must remember this kind of connection, that your reference phase should be the same for both wattmeters. Any doubts? Okay. Achha. So I'm asking like, and none of you guys attended sir's problem solving session? You guys would have got a message, everything, right?
Yes.
Hmm?
सर ये स्क्रीन में कुछ प्रॉब्लम है क्या सर? तो फुल स्क्रीन दिखाई नहीं दे रहा।
सॉरी सॉरी।
बोल रहे हैं कि स्क्रीन में कुछ प्रॉब्लम है क्या? वो मतलब फुल स्क्रीन दिखाई नहीं दे रहा वो। तो आपका दिखाई नहीं।
किसका? मेरा स्क्रीन फुल स्क्रीन नहीं दिख रहा है क्या?
हाँ हाँ, वो आपका पिक्चर आ जा रहा है तो थोड़ा सा बैक साइड में वो दिखाई नहीं दे
अच्छा, अभी?
रहा। हाँ अभी तो है सर स्क्रीन में, लेकिन अभी साइड में है अभी।
नहीं, मेरा पिक्चर कहाँ पे है? राइट पे है।
आपका आपका पिक्चर दो जगह है।
दो जगह पे है क्या? अच्छा अच्छा,
हाँ
एक
हाँ।
मिनट। अभी अभी ठीक है।
हाँ ठीक है सर अभी।
अच्छा अच्छा, ठीक है, कुछ तो प्रॉब्लम किया होगा। अच्छा, ओके। So after this, sir taught, after this, what did sir teach? Sir taught potentiometer. So why do we use a potentiometer? Hmm? So potentiometer is basically constructed. There will be some certain source will be there. Okay, some certain source plus minus some E1. Let us assume that will be connected to some point. Then let us draw. There will be some wire of some certain length L. Okay, let us assume there's a wire of certain length L. Then we want to measure some voltage Ex. So what will we do is we have to connect this by some jockey. Sorry. Ex. There will also be a galvanometer which will measure how much current is flowing. And then we'll connect it by certain some jockey J. So at some particular point, what will happen? That the current to the galvanometer will show zero. That is known as your null condition. And when the null condition is reached, it means that over here, that from here to here, that means from here to here, it is this voltage Ex. Okay, only when this voltage is Ex, then only there will be no current flowing through the galvanometer. And when there's no current flowing, then we will know, we will measure this length. With this length, we will measure certain L. And so we can find my Ex is equal to L upon capital L into E1. Any doubts in this? Hmm? So that's how we can measure what is this voltage over here. What is this Ex? We can measure through this method. So what we must have an ion is on the galvanometer. We must have an on the eye on the galvanometer. When we see that the current to the galvanometer is zero, that means it has reached a condition where it is sort of balanced. And we have to note down what is that length small l, and we already know what is the length capital L, and then we know what is E1, then we can get what is the effective Ex. Okay, so this is the actual basic, this is the basic idea of the potentiometer. there are various other things which are added to it, like how we must calibrate it properly. There can also be certain resistance drops can be there. So if there are those drops, how we should have an actual proper standard voltage source, which will help us to accurately calibrate the length and the distance. That is how much voltage per length. Okay. Once we properly calibrate it, then we actually connect with the voltage which we want to measure it. And then we move the jockey until we find a condition where the current flows is zero. Okay. So like there are many things can happen. Like you could have certain resistance drop over here. Okay. Or over here. This resistance drop is there. Huh. But we don't want it to be there. Or we acknowledge that those resistance drops are there. And so we will have to use what is known as a standard voltage source. Like a standard voltage source will have to be used. Okay. And we can set how much is this L by L into L by L in, sorry, we can set how much is this? What's it about? How much E1 by L we need by having certain resistance over here, which we can vary how much current flows. Okay, there are various advanced things to the potentiometer which are there, but the basic concept is we want to find certain voltage per length, and using that constant, we can move the jockey or we can move the key, and then we can locate a position at where the voltage which we want to measure is equal to the voltage across that particular length. And so then we can get an idea or estimate of what is the voltage which we want to measure. Okay. The standard voltage source also should be something whose voltage does not change with time, or it does not change with current, etc. So there are many other things are there. So this is we have considered for DC, but there could also be an AC potentiometer when we want to measure AC voltage. When you want to measure AC voltage, it becomes further complicated. Why? Because you might have a supply. Let us say your V supply is 230 volt. You have a multimeter and you measure your V supply is 230 volt, and you want to check some V source whose voltage you want to measure. That also suppose it comes out to be 230 volt. Okay. And then when you connect them, you will find certain current is flowing. Why is that? Why that may happen is because suppose you have one voltage like this. Okay. So let us say this is your V1 and this is your V2. So your V1 RMS will be 230 volt. Your V2 RMS also is 230 volt, but they are not in phase. There is certain phase shift. And because of that phase shift, what will happen is certain current will flow. Now, so when that current, so that would mean even though your RMS value of the voltage which you want to measure is the same and you have got an idea, but still you cannot get that null condition because there is a phase shift. So what you have to do in that case is you will have to use what is known as a phase shifter. So what will your phase shifter do is it will make this to come in phase. Let me draw it somewhere. It will cause it to come in phase with this. Okay. So you have supply V1. Okay, AC supply V1. It will go to what is known as a phase shifter. You'll have a round thing and certain knob which you can move. And the output of that will be this V3. Okay, the red trace, which is in phase. So you, by shifting the knob in the phase shifter, you can change the phase of the voltage such that it becomes in phase with your supply. So this is there, and okay. Another thing is, how do you achieve this? How do you get this sort of phase shift? How do you achieve phase shift? Okay. Suppose you have certain voltage V1 and you have a resistor. This voltage V2, so your V2 will be in phase with V1. But in case you have this V1 and you have a capacitor, certain resistor, and then you have another resistor, and then you measure this voltage V2. Now what will you see? What you will see is, if this is your V1 phasor, your V2 phasor will be leading it by a certain angle. Okay, it will lead. And why this happens? Can anyone tell me why? Like sir was saying, no, capacitor is there, resistor is there, which will vary. And so the phase shift will vary. Does anyone have an idea why it is happening? So there is actually some current which is flowing. That current which is flowing actually is V1 upon, let us say, this R1 C1. So this R1 plus R plus 1 upon J omega C1. Okay. So what will happen is, we know in a capacitor, the current leads the voltage. So this current I becomes a leading current. It is a leading current. Okay. So this current I leads V1. And now your V2 is equal to I into R. And because I is leading V1 and R is just a constant, so your V2 will lead V1. So how do you draw it is, let me minimize it a bit. This is your reference phasor V1. This is your current I, right? And then this is your phasor V2. So why is your current I leading? Because it is a capacitive circuit, because there is a capacitor. It is more, the capacitive component is larger than the inductive component. We assume that the inductance is negligible. So because it is an RC system, the current to the capacitor leads. So that's why the effective current is leading your input voltage. And because that current is leading your voltage, and when that current flows through this resistor, the drop, that voltage across the resistor will lead your input voltage. Okay. So any queries in this? Any doubts in this? Okay. So if your C is made very large, it could come in a state where this is your V1, this is your I, this 90° in phase out of leading, and this will be your V2. Okay. So such things is possible. This is the desired condition that we, like sir was saying, you want to achieve a 90-degree phase shift. That is the desired condition. In that case, what should happen? Your C should be very high. Your C should increase. It may not always be possible, but this is what we desire. So we represent AC quantities by a phasor. Okay, by a phasor, we represent AC quantities. Like suppose we have certain voltage V that we represent it as, we can represent it either as some x plus iy, where x is the real part, y is the imaginary component of that. Sorry, it can be x plus jy. For phasor, we use j. Or we can write V as R angle theta, where R is the effective magnitude and theta is the phase. Okay. So this is a common thing. You will have to use gate calculator, so you will not have that imaginary phasor concept available. So you'll have to know these things and how to use them. Okay, so let me assume you have your V1, it is x1 plus j y1, and your V2 is x2 plus j y2. What you will write it as, V1 is equal to R1 angle theta 1, and your V2 is equal to R2 angle theta 2. So if you want to do V1 into V2, you have two options. You could either do x1 plus j y1 into x2 plus j y2 and then expand and do everything. It will get a bit complicated. Instead, what you can do, it is actually equal to R1 into R2 angle of theta 1 plus theta 2. So this is an easier option. Now, if you want to do V1 plus V2, you cannot do R1 angle theta 1 plus R2 angle theta 2. You have to, instead you have to do x1 plus jy1 plus x2 plus jy2. And then you write it as x1 plus x2 plus jy1 plus y2. Okay. So in different scenarios, you'll have to use different methods, different representations of the same quantity to get the answer. Oh. Because in that gate calculator, you do not have the direct option of using phasors. At least in my time, it was not there. Oh. Okay. Also, this meeting will end in 2 minutes. So once this meeting will end, I will again restart this meeting so you can again rejoin. So till here,
Okay,
any
sir.
doubts?
No, sir.
Any doubts or queries? So then we will start with the
No, sir.
examples. Let's step in. So all of you have your calculator with you? Okay, I hope you guys all have your calculator because you have to do the calculations. Okay. So, okay. So what is given over here? We are told that there's a 240 volt single phase induction type energy meter. It is designed to make 150 revolutions of disk for every kilowatt hour of energy. So we have to calculate how many number of revolutions it will take when it is connected to a load drawing 30 ampere at 0.85 power factor for 2 hours. For 2 hours. Okay. So we have been told that it is a 240 volt. Okay. It is a single phase. It is an energy meter. It is designed to make 150 revolutions of disk for every kilowatt hour of energy. So if it will measure 1 kilowatt hour of energy, it will make 150 revolutions. Okay, they are saying it is connected to a load which is drawing current of 30 ampere at a power factor of 0.85 for time 2 hours. So now they are first asking how many revolutions you expect it to make. So how much power is it consuming? Power is how much? What is the formula for power? Can anyone tell?
VI
Sorry?
cos theta. VI cos theta.
Yes. So power actually is VI cos theta. Cos theta is your power factor. Okay. So actually it is, what is your V? It is 240. Current is 30. And the power factor is 0.85. So how much is this power? Can you calculate and tell me? Okay. No, now revolution is like you have one disk, right? It will rotate. It will rotate. So how many revolutions it takes? Like how many times it has rotated? Say you have your disk. Let me make it better. I have my disk. Okay. It has a red part over here. If it is rotating in this direction, let us assume. So after some time, how it will be? It will be like this with a red point over here. After some time, it will be like this with a red point over here. After some time, it will be like this with a red point over here. Okay. Finally, it will go back to its original position. So once it has gone back over the entire cycle and reached the original position, that is your one revolution. Okay. So what is your power? Calculate and tell me.
6120, sir.
120.
No, sir, 6120.
Okay, good. Thank you. So it is 612.
Yeah, correct, sir.
Okay, good.
20.
6120.
Yes.
What? It's in what? What's the unit?
Watts.
Okay, watts. Now, how much is the energy used? Energy consumed. How much is the energy consumed? We know energy is actually equal to power into time.
Yes.
So time is 2 hours. So what is the energy consumed? Huh? Simply calculate the mistake. No. Tell me. How much is it? Sorry. So how much is the energy? Mm-hmm. You guys have calculated, you calculate such a complex.
12,240.
Yes, yes. So it will be
12,240, sir.
12,240. 12,240. Okay.
Yes, sir.
12,240.
240.
Yes. What is the unit? Like this is in watts. What is this unit?
Watt hour.
Yes, it is watt hour. Okay. Now we want to convert it into kilowatt hour. So what should we do?
Divide by 1000.
Yes. So we have to make it 12,240 divided by 1000 gives us in kilowatt hours. So how much is that?
12.240.
So it becomes 12.24 kilowatt hour. Now we were told that if it consumes 1 kilowatt hour, it will measure, it will complete 150 revolutions. Now if it consumes, it has measured 12.24 kilowatt hour, it will go through X revolutions. So what is the value of X? Hmm?
Sir, 0.0816.
0.018. 0.018. Achha, what about others? How much did you others get? So actually what happens in this case is you have to do it is directly proportional. So your 1 kilowatt hour upon your 12.24 kilowatt hour is equal to your 150 revolution divided by your X revolution. Okay. So revolution gets cut. This also gets cut. So you effectively get your 1 by 12.24 is equal to your 150 by X. So your X actually is equal to 150 into 12.24. Okay. So now can you calculate and tell me what is your value of X?
So
1836.
1836.
Okay, 1836.
36.
Okay. So it has measured so it should measure 1836 revolutions. Okay. So others have any doubt till here? Or is it clear? Anyone? So if this energy meter was accurate, okay, the number of revolutions which it should measure should be 1836. But as in all practical real life instruments and devices, there is error, there are tolerances. Huh. So this instrument also has errors. And it actually made, instead of making 1836 revolutions, it made 1775 revolutions. So it had actually, how many revolutions it actually had measured was, or actually which it did was 1775. Okay, there can be lots of different reasons for that. It could be your calibration was not proper, or the instrument has over time it has become less accurate. It has also lifespan. It has decayed. Some mechanical things have become loose, or they have become, there's more friction is there. Many things can be there. So actually, it did 1775 revolutions, when in actual reality, it should, if it was properly accurate 100%, it should have done 1836 revolutions. So now we want to measure how much error is there. So in the question, what they're saying is, if the meter actually makes 1775 revolutions, then estimate the error as percentage of the actual energy consumed. Okay, actual energy consumed, and enter a positive number. So when you're giving your exam, whether you're all all types of exams, your college or your gate exam or your NPTEL exam, you must read the question very, very properly. So they are saying you must find a percentage of the actual energy consumed. So your number of revolutions which it measures is a indicator of how much energy it has consumed. Okay. So now also they have, so we have been told to find the error. Okay, error we can find out. We know the formula. We'll find out. And then they have told enter a positive value. And they've told to find the error percentage. So now, what is my error? My error actually is equal to how much it should truly be minus how much it turned out to measure because it is a faulty instrument. Divided by the actual energy is N true. Okay. So this is 1836 minus 1775 by 1836 and into 100. Okay, because we want percentage error. So how much is this? Can you calculate and tell me?
0.08
0.0
onwards.
0.87.
0.3, sir.
0.3. Okay. What about others? Hmm. What happened to others? Muthu,
3.33 I got.
you got 3 point?
3.3, 3.32.
Okay. Okay. So actually it is 3.32%. So Niranjan, actually, I think probably you missed multiplying some. Hmm.
Okay, sir.
Yes. Yeah. So it is 3.32%. So this much is the error which was there in our instrument. Now, what is the next part of the question? So you must select the correct statement. Does it measure more? Is the measured energy more than the actual energy consumed, or the measured energy is less than the actual energy consumed? Who can tell me? That is the instrument. How much energy it measured? Is it more than the actual energy which it consumed, or was the measured energy less than the actual energy consumed? Which of the options is correct?
Yes, sir.
A, yeah, the measured energy is more than the actual energy consumed.
Yes, sir.
Okay, so sorry. So your measured energy actually was 1775, but the true energy which was consumed is actually 1836. So the actual energy which was consumed is greater than the measured energy. Okay. So if you guys in your house, would you want such an energy meter? Yes or no? As a joking matter, you can tell yes or no, why, everything. You can talk. We have an energy meter where the actual energy is consumed is more than how much it is measuring. So do you want it
Yes,
or
sir.
not? Yeah. So suppose you are actually using 11 units and it will say you have used only 10 units. So your bill will be less, right?
Yes, sir.
Huh? So this would be a very good instrument. Huh? If you guys such
For
a
us,
uh, so bill will be less. You can use AC for more time. You can use TV, everything for more time. Hmm. Okay. So now we go to the next question. Acha. Let me take a screenshot. So we have such a thing. There is a circuit which is shown over here. Ammeter A1 reads 5.75 ampere. So this is current I1. This is current I2, and this is current I3. Okay. I1 it measures to be equal to 5.75 ampere. I2 it measures comes out to be 3.25 ampere. I3 comes out to be 8.25 ampere. So is anything fishy about this? Does anyone have any doubts? Why is it like this? What is going wrong? Hmm? Hmm. So what if you apply KCL over here? What does your KCL say?
I3 equal to I2 plus I1.
I3 is equal to I2 plus I1. Do what is I2 plus I1? How much is I2 plus I1?
8,
No, I2 plus I1 is 9.
9, 9, 9, 9,
Hmm.
9.
So your I2 plus I1 is 9. But how is your I3 8.25?
There will be error.
Huh?
There will be error.
Okay, error in the ammeter. Like how we wanted some kind of energy meter which has error. Now we got an ammeter also which has error. Okay, that's an explanation. So what you must understand that this is an AC circuit. Okay, this is an AC circuit. So the current which it is measuring is your RMS value. It is not measuring the instantaneous current. Hmm? Instantaneously your KCL will be followed. But for RMS values, your KCL will not be followed. Because the currents have certain phase, right? The currents have certain phase. So this is an AC circuit. And your R is given to be, your R is 700 ohm. Okay. So now they are saying the ammeters are ideal. What do you mean by ideal? It means the input impedance, that is the internal impedance of the ammeter is very low. That is the ammeter's impedance is all low. And we can assume that it is very accurate. It is 100% accurate. They told the ammeter is ideal. Ideal means it is 100% accurate. So we cannot say that ammeter is measuring wrong. It is measuring correctly. But still our KCL is not being followed. So the reason is because in AC circuits, you have to do phasor addition. You cannot do RMS addition. You have to do phasor addition is important. So it actually is your I3 bar. That is the phasor I3 is actually your I1 bar plus I2 bar. Okay, so phasor, as you know, I1 will be some 5.75 into some angle theta 1. Your I2 will be equal to some 3.25 into your angle theta 2. And your I, okay, this is bar. And your I3 bar is equal to 8.25 into some angle theta 3. Hmm? Clear? Any doubts?
No, sir.
So now this becomes complicated. How do you know what is theta 1, theta 2, and theta 3? You don't know. It is a big issue. You don't know what they are, right? So what you do is, in this circuit, you will take one phasor to be your reference. So one easy thing to take as my reference is through your resistor. Okay. There's a current flowing. When current flows through resistor, what will happen? There will be what? When current
In
flows
same
through,
phase,
sorry,
in same phase, sir. In same phase, current will be voltage.
there will be some voltage will come. When current flows through resistor, there will be some voltage drop, right? So let us assume that a current will generate a voltage drop V. And that current will be in phase. The voltage and the current will be in phase. Yes, I think you're saying in phase, right? So you're correct. So now we will have a reference phasor I2. And in phase with that, there will be a phasor V, which is equal to your I2 into R. Okay, this is your phasor V and I2 into R. Any doubts still here?
No, sir.
Okay. Now, what is your I1? Your I1 is actually your V by Z, right? This is actually V by Z.
Right,
Hmm.
sir.
So I will assume that it is a inductive load. So let me how do I make this? So this is my I2. Okay. So your I1 is equal to your V by Z in terms of magnitude, but it will have certain angle also. So we will take your I1 be something like this. This is your I1. Is lagging by an angle theta. Okay. Any doubts till this part? Okay. What will be your I3? So this will be your I3. Okay. So I3 actually is, this is your I2, or this is your I1. Yes, it is a phasor sum. Okay, it actually is a phasor sum. Hmm. So your I3 is actually equal to square root of, what is the formula for first phasor sum? Hmm?
I1 square plus I2.
I1 square plus I2 square. Then after that,
Plus I1 into I2. 2 I2. 2 I1 plus I2.
then
Cos theta. Angle between I1 and I2.
yes. So theta output is the angle between I1 and I2. So now can you find out what is, now what do you know? What do you know what is I3? You know, right? I3 is your 8.25. This is your 8.25 is equal to square root of 5.75 square plus 3.25 square plus 2 into I1 is 5.75 into 3.25 into cos theta. So can you find what is cos theta? any of you are there? Niranjan, Muthu, Vanchini, Devi. How much you got cost theta? Hmm? So cos theta actually is 8.25 square minus 5.75 square minus 3.25 square divided by 2 into 5.75 into 3.25. So how much is this? Hmm? You guys don't have calculator? Hmm? None of you? Muthu, Niranjan, Vanchini, Devi? Okay, but no, I have no calculator. Okay. So what others? So the answer actually comes out to be 0.6538. Okay, so this is your cos theta. Now, this is your Z. How much is your Z? Z actually is your V by I, V by I1, right? So your magnitude of your Z is equal to V by magnitude of I1. Hmm? What is your V? V we know is it is I2 into R. So that is equal to 3.25 into 700 divided by I1, it is 5.75. So can you find what is Z? Mhm. You can also put in the chat. You guys know what the answer? Okay, it comes out to be 395.652 ohms. All right. So I prefer if you guys could do the calculations. Maybe good practice for you guys only. Hmm? They want us to find the impedance, the power consumed by the impedance, and the power factor. Okay. So how much is the power consumed by this impedance? Can anyone tell? We found Z. to be 395.65 ohm. And here the current I1 is actually your 5.75 ampere. We know the cos theta is 0.6538. Okay. So your R actually is equal to your Z into cos theta. So that actually is equal to 395.65 into 0.6538. So your R comes out to be 258.67 ohm. So the power comes out to be I1 square R. So that is 5.75 square into 258.67. So that answer comes out to be 8552.52 watts. Okay. So any questions still about this sum which we have done? Any questions in it? No questions? To Niranjan, Vanchini Devi, no questions? Okay, if there's no question, I'll proceed to the next sum. Okay, so now we have this question where we have a resistance of a potentiometer wire AP is 20 ohm. So we are given that RAB is 20 ohm. We are given that E supply is 4.6 volt. And this test cell, E test, is 1.38 volt. And this R test is actually 11 ohm. So now what they are saying, asking us is find the null position in terms of the wire resistance R in ohm on the left of the jockey. So they are saying at which length R will this jockey be balanced? How to find V value? Okay, Mutul is asking question how to find V value. So in the previous question, we know I2. I2 is given to be 3.25 ampere, right? And we also have been given R is 700 ohm. So it's your voltage is actually equal to I into R, right? That is I2 into R. So that is how I multiplied I2 3.25 into 700 and I got my voltage. I didn't calculate it, but it is 3.25 into 700. So any other has that cleared your doubt, Muthu?
Yes, sir.
Okay, great. So now we have to find where I put the jockey. Should I place my jockey here or here or here? At what length of R will the jockey show null deflection? Okay, good. So now when will this happen? When your I test, you want I test to be 0 ampere. If your I test is 0 ampere, then what is the voltage over here? that voltage, because if your I test is 0, then voltage drop across R test also will be 0. I test into R test is 0. So the voltage which will come across your length R, voltage across the length R is actually equal to your E test. Okay, that is equal to your 1.38 volt. That is fine. So now all the current which was flowing like this will flow like this, and like this. The current I test is 0. So all the current flows like this. So the voltage at this point, whatever point, is actually equal to your, how much it is? So your E test should be equal to your current I which is flowing. This is the current I supply. So it should be equal to your current I supply into your R, right? But what is your I supply current? That is equal to your E supply by the resistance of AB into this R, right? Your E test, is 1.38. Your E supply, was 4.6. Your RAB was 20 ohm. So this is your small r. So your R turns out to be 20 into 1.38 divided by 4.6. So how much is this resistance? So the R comes out to be equal to 6 ohm. So your R is 6 ohm. Any doubts in this?
Six ohm.
Yeah, 6 ohm, correct.
सर ये जो कंडीशन लिखे हैं ये मतलब जब आई जी इक्वल टू 0 रहेगा वो कंडीशन है ना?
हाँ, सिर्फ वही कंडीशन पे है।
Yes.
उन्होंने पूछा कि नल कंडीशन के लिए आर क्या रहना चाहिए। नल कंडीशन मतलब आई टेस्ट इक्वल टू 0।
Yes.
Okay. So now they are saying is, if the jockey is moved rightward towards a distance corresponding to 1 ohm from the null position, then estimated test cell current I test in milliampere, answer with proper sign. Okay. So what they are saying is, the suppose the correct point was over here, but it is moved rightward such that the resistance R becomes 1 ohm. So it is moved in this direction. Suppose it is now placed over here. Then how will your circuit look, and what is your test current which will flow? So what we will do is, we will redraw this circuit. So now your circuit will become, this is your E supply, that is 4.6 volt, right? This is your R, this is your 20 minus R. This is your E test. This is your R test. This is your galvanometer, whose resistance is negligible. And this is where your jockey is placed. Okay. Your I test will flow like this. This is your I test. This is your I supply. Right? So now we have to solve this circuit. They told the resistance is moved 1 ohm to the right. So R becomes equal to 7. So this becomes equal to 13 ohm. Right? So now we must find what is my I test. So what I will do is I'll apply KVL in mesh 1. So it is minus plus E supply, and E supply is given as 4.6. So 4.6 minus I supply into this 13 ohm. So minus 13 into I supply. Then minus 7. Okay, then minus 7 ohm resistance into what is the current which is flowing? Your I supply plus I test. So it is I supply plus I test. This entire current is equal to 0. Right? So it becomes 4.6 minus 20 I supply minus 7 I test is equal to 0. So your 20 I supply plus 7 I test is equal to 4.6. This is your equation 1. Any doubts in this? Okay. So now I will apply KVL in mesh 2. So what I will get, minus plus E test, that is 1.38. Minus R test is 11 ohm. So minus 11 into I test. And then flow through the 7 ohm resistor. So minus 7 into your I test plus I supply. This is equal to 0. So I'll go to next page. So that will be equal to your 1.38 will be equal to your 18 into I test plus 7 into I supply. This is your equation 2. Any doubts in this much till now? So what do we need to find? We need to find I test. So what I will do is I will substitute the value of I supply in this equation to get the value of I test. So I'll write 1.38 is equal to 18 into I test plus 7 to this equation. I want I supply. So what is I supply? It is equal to 4.6 minus 7 I test upon 20. So what I will do is I will do 1.38 into 20 is equal to 18 into 20 into I test plus 7 into 4.6 minus 49 into I test. Right? So what is 1.38 into 20? This is 27.6 is equal to 18 into 20 is 900 I test. 7 into 4.6 comes out to be 32.2 minus 49 I test. So what it becomes 27.6 minus 32.2 is equal to 900 minus 49. That becomes 851. 851 I test. This becomes 27.6 minus 32.2. It is minus 4.6 is equal to 851 I test. Okay. So your I test is equal to minus 4.6 upon 851. So that comes out to be minus 5.405 into 10 to the power minus 3 ampere. So your I test comes out to be equal to minus 5.4 milliampere. Okay.
सर
हम्म,
टेस्ट 18 दूनी 36 मतलब 360 होगा ना सर?
क्या क्या क्या
आई टेस्ट जो कैलकुलेट किए हैं सर 18 दूनी 36
हाँ
360
हाँ
होगा ना सर?
18
900 आई 900 आई टेस्ट
हाँ 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 अच्छा वो
360
360
होगा ना
ओके
सर?
वो 360 होगा अच्छा अच्छा वही गलती है ना सॉरी सॉरी so that is 360 minus 49 is 311 hmm. So that becomes equal to I'll just rub all this minus 0.01479 ampere. So that actually is equal to minus 14.79 milliampere. Okay. Any doubts? Hmm?
No.
Okay, good. So actually, Vanshini Devi doesn't respond at all. I don't know what is the thing. Muthu is responding. Hmm. Even Niranjan is responding. Okay. So you guys are able to see the notes and everything, right? Where I upload everything. You have the links. I'll just share it once more. Hmm.
Yes sir. So in the chat, I have put the drive link where these notes I'll convert into PDF and upload it so you can refer later also. And the YouTube channel link where I will upload the video after merging the videos, everything. Okay. So you can refer to this later on also. Hmm. So now the next question, one question is moving it rightward. Next question is if I move it leftward. Okay, so that you can easily solve. Hmm. It is something similar. So the YouTube video by tomorrow I should upload it. It actually takes a little bit of time because I have to merge it, I have to edit it, then I have to export it, and then I have to upload it on YouTube. It takes a little bit of time, the video. The notes, it will be uploaded by today. Okay. So just bear a little patient. It doesn't happen instantaneously. So in the next case, they're saying the jockey is moved leftward. So if the jockey is moved leftward, what will happen is this R instead of being 7 ohm, it will become 5 ohm. And this will become 15 ohm. And then you'll have to solve. Okay. So it is actually very simple. We could actually just modify these equations also. It could actually be 4.6 minus 20 I supply minus 5 I test, etc. So you will have to solve this is your E supply, this is your 5 ohm, this is your 15 ohm, this is your I supply, right? This is your 1.38 volt. This is your 11 ohm resistor. This is your galvanometer, which you neglected. and this is your I test. So you can similarly solve, you can do it off. You will get for mesh 1, it will be 4.6 is equal to 20 into I supply plus 5 into I test. And your 1.38 will be equal to your 1.38 will actually be equal to 16 into I test plus 5 into I supply. Okay. So we need to find I test. So 1.38 is equal to 16 into I test plus 5 into I supply can be written as 4.6 minus 5 I test upon 20 I supply. Okay. So 5 and 20 becomes 4. It is 1.38 is equal to 16 into I test. That's 4.6 minus 5 I test upon 4. So your 1.38 is equal to 16 into I test plus 1.1 4.6 divided by 4. It is 1.15 minus 1.25 I test. So that is actually equal to 1.38 minus 1.15. It becomes 0.23. And 16 minus 1.25 becomes 14.75 I test. So your I test becomes equal to 0.23 divided by 14.75. That becomes equal to your 0.01559 ampere or 15.59 milliampere. Okay. So any doubts in this?
No, sir.
Okay, good. We'll start with the next part. So you guys are doing your BTech or you guys are doing your preparing for GATE? Like, what are you guys up to? Where are you guys studying or working? You guys can tell. Okay, Niranjan is doing BTech. What about others? Okay, Niranjan is doing BTech as a working professional. And what about Muthu and Vanchini Devi? Don't be so shy. You can tell me. Okay, they're doing something top secret, so they are not telling. It's fine. So let us consider Kelvin-Varley decade potential divider, which has 4 stages. It has 4 stages. So the resistance in the first stage is 10,000 ohm. Okay, resistance in the first stage is 10,000 ohm. How much will be the value of each resistance in ohm in the last stage? So what actually happens is in a Kelvin-Varley potentiometer is there be like R1 dot dot dot, so many R1s will be there. There will effectively be 11 R1s. Okay. Then in between there are two R1s, we will take their output and it will go to the next stage, which has R2 and then dot 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 many R2s. And at the end, there's 11th R2. Okay. So there are 11 R1s. There are also 11 R2s. And between two of the R2, we will take the next set, which will go R3. Again, there are 11 R3s. And in between two of the R3s, we will take it. And then finally over here, there will be 10 R4s. Okay. This actually is your R4, the final stage. So this is your where your V in will come. This is where your there will be some plate, some output from here. With respect to this, you will get your V output. Okay. So any doubts in this part? This is a complicated thing, but I'd like you to understand. No doubts? So what actually happens in the Kelvin-Varley connection is, okay, so this is the first stage. This is the first stage. Then there's a second stage, third stage, and the final stage. First stage, second stage, third stage all have 11 sets of resistors. The final stage has 10 resistors or 10 R4. Okay. Now, each time we take it across two resistors. Okay. And we want that 2R3 should be equal to 10R4. Okay. Effectively, we want 2R3 should be equal to 10R4. They told resistance in the first stage. Okay, first stage. So this in the first stage, it is R1. So your R1 is equal to 10,000 ohm. So we want, so what happens is your R4 is actually equal to R3 upon 5. Right? 2R3 is equal to 10R4. So your R4 is equal to R3 upon 5. So what it does is, effectively across this part, you will get a resistance of only R3. Because 2R3 parallel to 10R4, which is equal to 2. So what we have is 2R3, which is parallel to 10R4, which actually is equal to 2R3 parallel to 2R3, which actually is equal to R3. So this entire part is equivalent to a single R3. So over here, effectively, you will see 10R3. So here we have 10R4. And because R3 and R4 are chosen with some specific relation, you will get R3 effectively over here. So across two R3s, you will 2R3 and a 10R4 combination, you will get an effective resistance of R3. And then that R3 in combination with 9 other R3s becomes equal to 10R3. And then you must choose 2R2 is equal to 10R3. So what happens? Your R2 is your R3 is equal to your R2 by 5. So what happens now again? Your 2R2 comes in parallel to 10R3. So that again becomes equivalent to 2R2 parallel to 2R2 becomes equal to R2. Now this R2 effective resistance across this part, R2 plus again 9R2 gives effective resistance of 10R2 seen from here. So that 10R2 in parallel to 2R1. So then you have 2R1 parallel to 10R2. And this 10R2 is equal to chosen to 2R1. So effectively you have 2R1 parallel to 2R1, which is equal to R1. So what you have a relation is 2R1 is equal to 10R2. So your R1 is equal to 5R2, or your R2 is equal to R1 upon 5. But we know that my R3 is equal to R2 upon 5. So this becomes R1 upon 25. I know my R4 is equal to R3 upon 5. So it becomes equal to R1 upon 125. Okay. So now my R1 is 10,000 ohm divided by 125. How much is this? So that becomes equal to 80 ohm. So any doubts in this?
Sir, और बार repeat कीजिए.
One वापस repeat करता हूँ. So this Kelvin parallel वाला ना. So this Kelvin-Varley connection will tap. It will tap from this point and this point. It will tap across two resistors for sure. In this case, and in this case, and in this case. Okay, this is the logic which that person who invented this thought. It should he designed it in such a way, and it is a very good design. So he designed it. So let us look from the final stage. In the final stage, there are 10 R4s are there, and here there are 11 R3s. Okay. So what he did, what he has decided is 10 R4 should be equal to 2 R3. Okay, 10 R4 is equal to 2 R3. So at this point, and so effectively at this point, okay, at this point, it is what? It is 10 R4 parallel to 2 R3. It is 10 R4 parallel to 2 R3. And because he chose 2 R3 is equal to 10 R4, you get the effective resistance R effective is equal to R3. Okay, you get your effective resistance R effective to be equal to R3. Now this is R3, but there were 11 R3s. So you're across 2 R3, because there's a parallel potential divider outside, it becomes effective resistance across that point becomes R3. So it becomes R3 plus the remaining 9 R3. So R3 plus remaining 9 R3 will result in the resistance over here to be equivalent to 10 R3. Equivalent to 10 R3. This is in parallel with 2 R2. Now again that same funda I will put that my 2 R2 is equal to 10 R3. Then again I will do the parallel combination and I will get that resistance to be R2. But there are remaining 9 R2 resistors are there. So 2 R2 resistors gets combined into an effective resistance of R2. So 9 R2 plus R2 becomes 10 R2. That is seen across this point. This point sees 10 R2. And that 10 R2 is set to be equal to 2 R1. And again, you will do that same logic. Okay. So is that clear? Good. So we'll go to the final sum. Shown here. So this is known as a coordinate potentiometer. Why it is known as a coordinate potentiometer is because whatever voltage we want to measure, we will divide it into real part and to an imaginary part. So this is the in phase means the real part. The quadrature phase is the imaginary part. Okay. So that is one point. So now what they have given is P1 and P2 are identical potentiometers. They each have a length of 12 meter and a wire resistance of 50 ohm. P1 is already standardized. Okay, P1 has already been calibrated, standardized, everything. And now we want to standardize the potentiometer P2. What we want to do is we want to change the currents, right? We know this M. M is equal to 102 millihenry. And the frequency is 60 hertz, right? So now what we have to do is, what actually is happening is, over here, what current will flow? Suppose there's some current flowing, let us say I1. And because of this R1, C1 combination also, we also want the same current I1 to flow. But this current I1 which will flow, this let us say this I2. Okay. We want I2 to be equal to I1 in terms of magnitude. But we want I2 to be equal to I1 angle 90. Or let me write, that is I2 will lead. It leads I1 by 90 degree. So now when this I2 will flow, it will also result in some current over here because it is coupled by an air core transformer. Okay. So these are all magnetically coupled with iron core. This is an air core transformer. Now the voltage which will come over here, that voltage is equal to your j omega m into I2. Okay. But this voltage over here, because of this length, VR is equal to I1 into R. So what is actually happening is your I1 into R is equal to your I2 into your omega m, right? And your I1 and I2 are equal. So that means your this R, whatever this resistance comes across this length, so that will be equal to your some small r in, no, that actually is equal to your 50 ohm. No, sorry. That actually is your R. The effective resistance is equal to your omega m. That is your 2 pi into 60 into m. Now this resistance R, actually it is equal to your, let us say what is the length is 12 meter. So it is some length L divided by 12 into your 50. And this length L is less than 12. So we need to find this length L. So we have L into 50 divided by 12 is equal to 2 pi into 60 into your M is how much? M is 102 millihenry. 102 into 10 to the power minus 3. Okay. So L is equal to 12 into 2 pi into 60 into 0.102 upon 50. So you can calculate how much it is. So your L comes out to be 9.228 meter. Okay. Any doubts in this?
R इक्वल टू जो लिखे हैं L by 2L.
Because
R
it is
equal to
no your total resistance. Your total resistance is for 12 meter. But this is your R. Your R is just a small part of it. So suppose your total resistance R total. Let me your R total is equal to 50 ohm for 12 meter, right? But your R for L is some value. So what do? You have this R is equal to your L into this 50 by 12. Okay. Because the total resistance is 50 ohm. But that is for 12 meter. But your length. So what I want to say is that a total resistance, this the resistance from here to here is 50 ohm. Okay, this color is not same. That total resistance is 50 ohm. Okay. But this R is just a small part of it. This R is just a small part of it. So how much is that resistance? It is a fraction of this total resistance. So what is that fraction? It is how much length is there divided by the total length is the fraction into that resistance 50 ohm. Okay. So any doubts you have regarding this session? Okay. Okay, then I'll end this meeting. Thank you for joining.